Right. Uh, so the today's lecture is on feedback amplifiers. But before I get into the feedback amplifiers, there were a couple of questions posted by uh, your friends earlier on. So let me first answer those questions. I have answered. I have given provided the answers to them, but I thought there may be others who may be uh, having the same questions also. So therefore, let me first go through it and then get to uh, the today's lecture. Okay. All right. The first question is by Chalani. When analyzing small signal H parameter model, can't we use H parameter conversion formula directly to convert common emitter H parameters to common base or common collector H parameters? I have found some derived conversion formula in the internet and they have used it directly when analyzing H parameter model. Do we need to prove the formula for current gain, voltage gain, input impedance and output impedance using H parameters, or can we directly use the derived formula when analyzing the problems? Right. So this is a good question. The question basically deals with whether you can use simplified or derived equation directly without going through the first principles to derive them. Well, if you are talking about an application, like in the industry, when you have to solve a problem, you may do it. But the issue in doing that is when deriving these relationships for formulae, we make certain assumptions. Right? For example, common emitter amplifier BJT common emitter H parameter model, we make the assumption that the HRE can be neglected. Right? There are some models which also neglect the HOE, right? The output impedance or output admittance. So these assumptions won't hold all the time, right? Under certain conditions they may work, under certain conditions they may not. So unless you can always verify that the formula that you use don't have any assumptions, then it is fine. But most of these formulae they base on certain assumptions. But obviously we cannot remember all these assumptions along with these formulae all the time. Therefore, it is not safe to use these derived formulae directly, right? Besides, deriving something from the first principles doesn't take too much time either. Most of the time, because they in order to derive something what you need is basically very simple things like either Thevenin equivalent circuits, Norton equivalent circuits, Kirchhoff's voltage law, current law, that kind of very simple things, right? So therefore we don't necessarily have to rely on some formula which was derived under certain conditions. If you don't satisfy these conditions, your answer will be wrong. So therefore I always advise, at least for this course, I do not expect you to remember these formulae. So you have to derive. If I ask you to do that, it will be after derivation. Right? Okay, so don't try to memorize them. Second question. That was the first question. The second question was by Tushara. In the amplifier configuration, we proved that voltage amplifiers should have a very high input impedance along with a very low output impedance. Keeping that in mind, when we look at the common collector configuration, it is biased such that the input impedance is very high and the output impedance is very low. So naturally, it has characteristics of a voltage amplifier. But common collector does not work as a voltage amplifier. Instead, it works as a current amplifier, which has opposite amplifier configurations. This problem also comes with the common base configuration. If you could please clarify this matter, I would be much obliged. Right. So thanks to Shara for asking that question. This is also again a very good question. Here, the issue is common emitter amplifier, BJT common emitter amplifier has moderate input impedance and moderate output impedance in the range of kilo ohms or tens of kilo ohms. Right. So these values are not very suitable for voltage amplifiers, but they have high voltage gain, which is something that we require in a voltage amplifier. On the other hand, for common collector amplifiers, they work as buffers. In other words, they have very high input impedance and very low output impedance, but they don't have any voltage gain. Voltage gain is 1 or slightly less than 1, 0.9 or 0.98, something like that. So therefore, obviously, it doesn't work as a voltage amplifier. It doesn't amplify the voltage, but it has good input and output impedance characteristics, so that when you connect it to a voltage source, it doesn't draw a current from the source, so that the voltage, full voltage, is applied across the input. Output, when you connect to a load, it doesn't drop too much voltage inside the amplifier itself. So therefore, these are some useful characteristics. So therefore, in order to actually build a good voltage amplifier with high input impedance, low output impedance, and also high voltage gain, you cannot achieve this just by using either a common emitter amplifier alone, or a common collect amplifier alone, or even a common base amplifier. So for this, what we do is we cascade. We use what are called multi-stage amplifiers, as we discussed in the multi-stage amplifier section also. uh, as initial stage, we use a common collector amplifier, so that it has a high input impedance, but it doesn't have high voltage gain. As the second stage, to achieve the high voltage gain, we connect in cascade a second stage of common emitter amplifier. So with that, we have with these two stages, we have a high input impedance and a high voltage gain, but output impedance is still not very low. So therefore, in order to achieve that, we then connect a third stage again from common collector configuration, so that the output impedance is also low. So that the first stage is common collector, second stage is common emitter, third stage is common collector again. So that we now have a low output impedance, high voltage gain, and a high input impedance characteristics. So this is basically how you achieve all three requirements for a voltage amplifier. And later you will see that instead of using JFETs, BJTs, we can use other types of amplifiers like field effect transistor amplifiers to even increase the input impedance further. Okay, so it will be discussed later on. Okay, so I hope that clarifies that question also. Okay, right. Tushara, was it clear?
Yes, sir. Thank
Okay, and Chalani, was the previous one?
Yes, sir.
Okay, right. Thank you. All right. So, any other questions before I start the lecture today? Any other questions? No. Okay. So let me then move on to the new section. This is on feedback amplifiers. Okay. Let me share my screen here. Okay. So before I so the today's section is feedback amplifiers. Right. So so far we have mainly looked at amplifiers which are called open loop amplifiers, right? There are some other type of amplifiers called closed loop amplifiers also. So therefore we are going to first look at these two concepts, open loop and closed loop amplifiers. In fact, though we say we mainly looked at open loop amplifiers, we have actually looked at closed loop amplifiers as well. In other words, feedback amplifiers. Uh, in When we talked about common emitter amplifiers with a emitter resistor, right? To stabilize the amplifier. Remember, to avoid thermal runaway, we used a small resistor in the emitter circuit, with a bypass capacitor of n. This basically we will see later that it's a feedback amplifier. Okay, so open loop and closed loop amplifiers. So an open loop amplifier is basically it doesn't have any information at the input based on the output. Okay, open loop amplifiers, no feedback from output to input. Okay, so therefore this is like, you feed something from the input and you get the output, and sometimes, if, for example, if the temperature varies, some of the parameters might change, but we don't really care about it. Output may vary. For example, if the temperature varies, the beta value changes. If the beta value changes, the current gain varies. If the current gain varies, the output voltage also varies. So without input being changed, output changes, right? Sometimes we don't really worry too much about that. Maybe the variation in temperature is too little, we don't have to worry about it, and things like that. But sometimes we do have to worry about it in most of the applications that we have. Now if you look at the beta value, just the beta value of a BJT amplifier, you will see that if you look at the data sheet, it is given as a range, not as a value. Though we use it as 100 or 50 or 200, that's not just one value. In fact, the beta, the current gain, varies in a very wide range. For example, for a transistor, beta can be from 50 to 400, depending on the temperature. So it's a very large range. It's not just one value. It's 50 and 400. It's almost like tenfold variation, right? So therefore, but these are practical values. And if you look at most of the electronic devices these days, they use amplifier these transistors that are that have beta values and other parameters that vary so much. And then how do they behave so reliably if that is the case, right? And this is basically achieved by using this feedback concept, right? Though these individual parameters may change, we can use this feedback concept to stabilize, to achieve very low sensitivity to external parameters, right? So for example, if you use feedback, you can improve the stability of voltage gain from about, let's say, 100% to maybe 0.5%, right? If the temperature varies, the gain otherwise would vary, like gain may be doubled, 100% variation on. But if you use feedback, you can make it so that it is very stable. It doesn't change at all, almost like, maybe if we want to set it at 10, it will be varying from 9.99 to 10.01. So it's very stable, right? So likewise, we can achieve this high stability uh, just using feedback amplifiers. This is basically what we are going to learn in this section, right? So the second type, which is very important, is called the closed loop amplifiers. Closed loop amplifiers. Now they use some of the output as feedback to the input. Okay, some of the amplifiers output is is fed back to the input, often as a negative feedback. Okay, that what that means is, if the output increases, input is reduced so that the output will be reduced. Okay, so that is called the negative feedback. On the other hand, if input increases when the output also increases, then it is called the positive feedback. That typically leads to unstable systems. Okay, it will quickly. This is what happens in if you remember, the thermal runaway was positive feedback. When the temperature went up, the current increased. That increased the temperature even further, right? So that was a positive feedback. Now, in negative feedback, we try uh, if the current increases, it will try to reduce the heat generation. That is what we try to achieve with negative feedback. Okay. So these closed loop amplifiers with feedback can achieve uh, many different desirable characteristics in amplifiers. For example, we can set a very specific and very stable gain, voltage gain or current gain, even under varying temperature conditions. Okay, and also even under varying transistor characteristics, as well as it will reduce the distortion will be reduced as well. When you remember, when there is non-linearity, obviously the BJT itself is a non-linear device, but we try to focus our attention within a very small region of the operation, so that is why we call it a small signal model, so that these non-linearities don't come into the picture. Now with this feedback, we can achieve very stable and um, operating points which are very small, so that their distortion due to nonlinearities is greatly reduced. Okay, and also it controls. There are other advantages, like we can reduce the effects of noise, right? As well as we can increase the input impedance and reduce the output impedance, or the other way around. If for a current amplifier, we can increase the output impedance and reduce the input impedance. So by controlling the way we do the feedback, we can improve the input output impedance, as well as we can improve the bandwidth. What are the frequencies that can actually get amplified using this amplifier? So these are all good properties, right? The characteristics are everything that we really like to have, but we get this at a cost. The cost is we are going to use lower gain. The gain will be less. So we trade off gain. Instead of 100, the gain will now be maybe 5 or maybe 10. So we reduce the gain to achieve these desirable properties. Also, when it comes to analysis, these feedback circuits will be much more complicated to analyze than the simple open loop amplifiers. Okay, so let me give some notes on that. Closed loop amps can achieve a very specific and stable gain with varying temperature and transistor characteristics. As well as much lower distortion. Okay, you can achieve much lower distortion. It also reduces effects of noise. Reduce the effects of noise. Controls input and output impedance. Increase bandwidth as well. but this at a lower gain. So the trade-off is gain. You trade off gain to achieve these uh, desirable properties. Also, uh, the analysis is more complicated. Okay, so that is the trade-off. Okay, now in multi-stage amplifiers, we uh, we discussed about this. So let me. This is not specific. The next thing that I'm going to talk about is not specific to feedback amplifiers, but to multi-stage amplifiers. But let me mention that here because I think I might have missed that point earlier. Now, when you increase the temperature, the transistor characteristics change. For example, beta value increases in most of the amplifiers. In addition to that, the base emitter voltage, VBE, also changes with temperature. Now, for NPN transistors and PNP transistors, they, if the VB increases in NPN, PNP reduces. So, therefore, often what we do to compensate the effects of these varying characteristics, what we do is we use NPN and PNP transistors both in the same circuit. So, for example, if you have two stages, one common emitter stage and another common collector stage, for one stage we use NPN transistors, for the other stage we used common collector transistors, so that the changes can be compensated, right? This is not necessarily, as I mentioned, uh, for the feedback amplifiers. This is true for any multi-stage amplifiers. Okay, so let me put this also. This is also another improvement. So improve temperature sensitivity. So that it is less sensitive to temperature variations. Sensitivity by using both NPN and PNP type transistors in the same circuit. Okay, so this cancels off VBE changes, VB effects. So VBE is dependent on temperature. Okay, these are mitigated by the above technique. Okay, so an example of a multi-stage closed loop amplifier. Let me draw one multi-stage. Now you don't have to always have multi-stage feedback, multi-stage closed loop. You can have a single stage and feedback amplifiers also. In fact, the common emitter amplifier with the emitter resistor was a single stage closed loop amplifier, right? But now I'm going to draw a multi-stage, two-stage amplifier with closed loop or feedback mechanism. Okay, closed loop amplifier example. Okay, so in this case, let me first have a common emitter stage like this, right? And the second stage of common collector, but this is going to be, so this first one is a common emitter, second one is a common collector, and also the second stage is a PNP transistor. The first one is NPN, second is a PNP, so that you achieve this temperature stabilization or temperature desensitivity due to varying VBE dependence. Okay, so this is the emitter. So this is a common collector. So you have the resistor connected to the emitter, not the collector. Right. So this is like that. So plus VCC, and the output is taken from here to a capacitor. So this is V out, and the input is given through a capacitor, and there may be a resistance also, source resistance it may be, and the biasing you do like this. Okay, so this is the ground. Now obviously like this it will not get biased, right? There is no positive connection here, so there is no biasing. So this is achieved through feedback. So to do that, what you do is you connect a resistor to the output, and here like this. So this is the feedback resistor RF. It works as a feedback resistor as well as the uh, biasing circuit. Right, you will see that. So RC1, and this is R1. Okay, so this is the input. So in this case, what happens is the biasing happens. So this resistor and this resistor along with this resistor will form the biasing circuit, right? So if you get rid of all the if you open circuit the capacitors, this RE, RF, and RB will be there. So there will be a DC current flowing through this. In fact, this voltage at this, the total current that flows through RE1 will not flow through RF, but there will be a certain voltage at the DC voltage at the emitter of the second stage. That will be kind of like the VCC for the first stage to set up the uh, biasing voltage. And the good thing is when you change, if for some reason if this voltage increases, if this voltage increases at the emitter of the second stage, then RB1 increases. The voltage across RB1 also increases because it will act like a voltage divider. The whole current flows through that. The current through the base will be very much smaller compared to that. So therefore, the voltage at the base will increase, and the increase of that voltage will increase the current through the first stage, and increase in the current will reduce the voltage at the collector, right? Because the voltage drop across RC1 will be greater, so that the voltage across the second stage will be less, and therefore output will be reduced. So that when you reduce the output, it will come to that. So this is the feedback mechanism. So the output will be when the output voltage increases, the biasing voltage will also increase, and it will reduce the output. So that is the feedback mechanism, right? So DC voltage is set by RF to RB1. Okay, so that will be we would like to have VCC by 2 as the preferred DC voltage. Okay, and the gain is set by RF to RC1. Okay, the RF to RC1, we are not going to analyze this at this stage, but we are going to see this is basically what is going to determine the gain of this circuit. Okay, right. This is a inverting amplifier with feedback. Okay, because the first one is a common emitter amplifier, which is an inverting amplifier. The second one is a buffer, which doesn't amplify, but just um, the gain will be one, positive one. So therefore, negative gain will be there. Okay, so that's basically what we have as an example. Now let's move on to the feedback amplifier feedback concept. Okay, now see the feedback concept. Now, so far, what we have seen is basically amplifiers. Like for example, it could be, let me mark it as a black box, basic amplifier, with maybe the transfer gain, forward transfer gain A. Now, why do I say just forward transfer gain? This remember, depending on the type of amplifier you have, you can have different value for A. For example, if this is a voltage amplifier, A will be just a scalar which determines the output voltage divided by input voltage. If this is a current amplifier, A is again a scalar that will be equal to the output current divided by the input current. But again, there are other types of amplifiers like transconductance and transimpedance amplifiers where A will be a ratio between a current and a voltage, or a voltage and a current. So therefore, that A may have units, either ohms or 1 ohms. Okay. So therefore, depending on the type of amplifier that you have inside this black box, you may have different values of transfer gains, right? You know, the input may be a current, output can be a voltage, or input can be a current and output can be a current, or likewise. So this is depending on the type of amplifier, you may have different configuration inside, but it can be either a current or a voltage. Okay, so this could be, input can be a current or voltage. Okay, this can be anything. The output of this, again, depending on the application, it can be a current or a voltage or a current. Okay, we don't know. Now this is your basic amplifier that we already know. This is without feedback. Now you may also have a signal source. Okay, this can be a voltage source or a current source, right? It can be a voltage or a current source. Whatever it is that we have is there. Okay, depending on the type of the source, it can have either a voltage output or a current output, constant value. The other parameter varies. Right, and also you have a load. Okay, you have a load. Typically, it's a resistor, right? But it can be some other load also. It can be non-resistive load also, capacitance, inductors. All these things are possible. Okay, so uh, this is the output. Okay, so again you will have either a voltage or a current as the load. Okay, so this is IO, or basically let me call it IL, load current. Okay, this is the load current. Right, now in feedback concept, what we do is basically we sample part of the output. Okay, so you put a sampling circuit here. Okay, you put a sampling circuit here. Sampling network. What it does is it gives out part of the output. Now, if you define the output as a current, the output will be a current. If you define it as the voltage, output is voltage, you will take a voltage, right? And then what you do is you basically take part of that output. So, okay, this is basically getting the output. This is the output directly. This is the output. So, the same output that you have there will be here. Okay, so this will be the voltage or current. We don't know what it is. The same thing that goes into the load. Okay, so this may be the current or the voltage. We don't know what it is. This is called the feedback network. Feedback network, and it has a what is called a reverse transmission gain of beta. Basically, the input to this network times beta will be available as the output. So this again, the output can be a voltage or a current that we don't know. Okay, so again, each of these blocks, the quantity that we control or the quantity that we are interested about may be either a voltage or a current. Uh, so so what we do is, now if for example the output may be a voltage, you take this you feed the output voltage to this feedback network, and output of this feedback network can be either a current or a voltage. Okay, so this feedback gain beta may be just a scalar. If the input is current and output is also current, then the beta is a scalar. Similarly, if the input is a voltage, output is also a voltage from this network, again beta is a scalar. But if the input is a voltage but the output is a current, then it will be it will have some units, right? Then what you do is you take this output of this feedback network and with the um, mix it with the input signal from the source. Okay, so this is the source signal. So we call this comparator or mixer circuit or mixer circuit. Okay, mixer circuit. So what you do is basically feed this here. Now in this doing so, there is one important thing that we need to remember. We mix it in such a way that it always mixes it in such a way that it reduces the input to the basic amplifier. So this value, so if without the comparator, if the signal was directly fed, the signal from the source is directly fed to the amplifier. Now what will happen is the IF will be subtracted from IF will be subtracted from IS to get II. Okay, if it's a voltage mixer, then VI will be equal to VS minus VF, not VS plus VF. So that is the important thing. So this is a negative feedback. So it will be reducing the input that was originally coming from the source based on the output. Okay, the part of the input will be reduced. So that is called the negative feedback. Okay, so this is basically the main setup that we have. Inside each of these blocks, you may have different kinds of things, right? For example, this can be a just a resistor. So this can be a voltage source. Okay, for example, this can be something like this. Okay, something like that. Right? So, and the amplifier may be a common emitter amplifier or maybe a op-amp circuit, whatever. It doesn't really matter. Now, in the good thing about this is we don't really care what is inside each of these things, especially inside this amplifier. We don't care. It can be a very complicated amplifier. It can be a single stage common emitter amplifier, two stage or three stage or multi stage amplifier, or it can be an op amp, whatever it is. Okay, so this is basically a more general concept than that. So if you look at each of these circuits, so what's inside this sampling circuit and what's inside this comparator? Okay, then you will see that the sampling network, the first one, the this one over here, okay, the sampling circuit. Now, the purpose of the sampling circuit is to get sample of the output. So, basically, what we want is a output. If the output is a current, you need a current output. If your output is a voltage, we need a voltage output. Right. So, if let's assume my output is a voltage. Okay. So, voltage sampling. So, we need to sample the output voltage. So, in for that, what you have is basically you have the amplifier with gain A. This is the amplifier without gain. Right. This is the original circuit that you had, and this is going to go to the load. This is the load. Okay, and I have the feedback circuit. Now, how do I sample the voltage? What I want is this should be equal to this. This is the V out, right? Output. Now I said my output is a voltage. So this is the V out. I want that exact voltage here. So how do you do that? The way to do that is you have to connect it like this. So that this is a parallel connection or shunt connection, right? You connect the load and the feedback network in parallel. So this is called a shunt connection or a parallel connection. So this is how you sample a voltage. On the other hand, if I wanted a current sample, okay, current sampling, then what I have is I have my uh, amplifier with a current with a gain of A whose output is a current, right? And I need a sample of that as the input to my. Remember, in this case, this is the input, this is the output of the feedback circuit. Okay, feedback network. The input to output is this direction. Okay, so this is the input, this is the output. Okay, whereas here it is the input of the amplifier is in out. Okay, so the feeding back, it is going in the other direction. And you have a load. This is the load RL. So the current is what we are interested about in this case. So the current I out goes to the load. Now I want a sample of that. In order to obtain a sample of that at this, what do I do? I have to take a series. You have to connect this circuit in series, right? So this needs to be connected in series like this, so that the same current flows to this I out. So this goes to this. So that is the input of the circuit. So this is called the current sampling. Hopefully this is clear. Okay. And similarly, for the second circuit, or this circuit here, the comparator mixer network, how do we get that, right? So now we already have this amplifier. So again, my input can be a current or a voltage, okay, and that depends on whether you if your input is input, you have to subtract. If your input is a voltage, you have to subtract a voltage from the input. You can't subtract a current from a voltage, right? So if your input is a voltage, the output of the feedback network beta network has to be a voltage. So even if your input is a current, you have to convert it into a voltage. If the input to the feedback network is a voltage, in other words, the output of the whole circuit is a voltage, which is what we fed back into the feedback network sampling circuit through the sampling circuit. But now, if my input is a voltage, I have to subtract a voltage from a voltage because I can't subtract a current from a voltage, right? So therefore, you need to have a voltage as the output of the feedback network. Typically, this value is an attenuated version of the input to the feedback network. Okay, so therefore, V out is the input to the feedback network. Output of the feedback network is Vf. That Vf has to be attenuated by a factor of beta. So beta is less than 1. So Vf is equal to beta times V out, where beta is just a number because input is a voltage, output is a voltage. But on the other hand, if input is a voltage, but my input to the whole circuit is a current source. If the current source, then I cannot subtract a voltage from a current source, right? So in that case, I need to have a current as the output of the feedback network. So IF should be the output of the beta network. So though the input to the beta network or the feedback network is a V out, it's a voltage, output has to be a current IF. So therefore, IF should be equals to beta times V out, meaning that my beta has units now. Okay, so for if you want to subtract a voltage, right? So for example, now I have a network. This is the amplifier. Now input to this amplifier is a voltage, let's assume. Okay, this is a in so Vi. So therefore my source is also a voltage source. This is my source. Now I have to get the output from the beta network also. So the feedback network, it has a gain of beta, whereas the input can be a voltage or a current, or it can be I out, whatever it is that you have, we don't know. But the output of this has to be subtracted from input. So this is Vs, right? So in that way, we need to subtract this from this. So let's call this my Vf in that direction. Then if I want to subtract this, how do we have to connect it? We have to connect it like this, so that this is Vs, right? Vs minus Vf is equal to, so Vf plus Vi is equal to Vs. In other words, Vs minus Vf is equal to Vi. Okay, so that is basically called the series mixer, because we are connecting the source and the feedback network in series. So this is called a series or voltage comparison, series mixer. Okay, so for these are for voltages. Okay, if the input signal is a voltage, this is what we should do. Okay, we should use a series mixer. On the other hand, a shunt mixer or parallel mixer is what we use for currents. In other words, we have a current source, so we represent it as a Norton's equivalent circuit. So this is my source, okay, and I have my amplifier with a gain A, which has a input current I. Okay, so input is a current I. Okay, that is what I have, and now I have to combine the output of the beta network. The input can be a current or voltage to this network, but output now is a current, right? Remember, it's a output of this network is a IF, because I need IF as the current. Okay, so in order to do this, what do I have to do? The way I connect this is, so I have to connect it in parallel, right? So initially there was a current IS going like that, out of which I have to take out some current, right? So therefore, part of this is going like that. So this is the direction of IF, and it is going like that. So IS minus IF is equal to II. Okay, so that is how I connect it in order to um, mix a current. So if the input to my amplifier is a current, I have to subtract a current. Then this is how I do it. Okay, hope this is clear. Any questions up to now? Any questions? So that we know what's inside this box and this box. Okay, that is basically what you have here. That's the sampling network box here. That's the sampling box here. Okay, so that is basically the sampler network, and this is the mixer network. Okay, so this is basically nothing but how you connect those. That's all, right? So inside these boxes, what you have is um, either a shunt connection or a series connection. That's all. All right. So now, since this feedback concept is not just valid for electrical quantities, voltages and currents. This is valid for any engineering quantity, like it could be the displacement, it could be the velocity, it could be the force, it could be anything, right? It can be any physical quantity, not just voltage and current. So therefore, we would this feedback concept is more general. It's way more general than just for voltages and currents. And then we use a notation rather than using two terminals to indicate in the reference and the the voltage terminals, the two terminals, because the voltage is always between two terminals. Rather than that, we use a single line diagrams like this. So in order to represent the amplifier, we represent the amplifier, which uh, basic amplifier we represent by gain, and the feedback network we again represent by a black box like that. And the comparator we simply mark like this, the comparator, and the input to that, there are two inputs to that comparator. One is positive, the other is negative. The addition of these two will go to the basic output, and that is my output, and I sample the output and feed it into the feedback. So this is how you draw it. So what is this? So whether it is current or voltage, if you want to, if you want to use a common notation, we call this the source input signal. So this is the input signal, XS. XS can be a current or a voltage. Okay. So this is the comparator or the mixture. Output of that is called the XD. So the input to one input is the source signal. This is the second input is the feedback signal, XF. But is XF is equal to beta times input to this circuit, which is X out. So this is X out. Beta times X out is the output of that. Now X out can be a current or voltage. XF can be a current or a voltage. XF and X out does not have to be the same type. So that while X out is a voltage, XF can be a current or a voltage. If XF and X out are both voltages, beta is a constant. Whereas if XF is a current, X out is a voltage, beta is 1 over ohms, right? Some conductance likewise. Okay, so the output of the mixer is the difference between the signal and XF. So therefore we call this XD, which is in fact the same as the input to my basic amplifier, which is equal to XI. Okay, so these are some notations that we use. Whereas X out is basically A times Xi, and this goes to the load, right? So that is basically the main way we draw it. And so if you try to write this down, XD is what? XD is the difference between the source signal XS and XF. And we define beta, the feedback reverse transmission factor, we define it as XF divided by X out. Okay, so this is called reverse transmission factor. It's called the reverse transmission factor beta. Like similarly, we define the gain of the basic amplifier A as the output divided by input, right? Transfer gain, forward transfer gain, okay, and the gain with feedback. So that is basically the output divided by XS. The total system, you can look at it as a system like this, right? So the input to that system is XS, output is X out, right? So that ratio we call gain with feedback. We define it as X out over XS, gain with feedback. That's it, gain with feedback. And you can, from this first equation, we can see that XD is equal to XI. Because XD is equal to XI, we can also write XS is equal to XI plus XF. Okay, the reason for that is XI is the same as XD. Okay, so therefore I can write XS is equal to x out divided by a from this equation, right? Xi is by x out divided by a plus what is xf? Xf from this equation I can write as beta times x naught. So I have everything written in terms of x out. So I can write this as 1 plus beta times a over a x out if I take everything to uh, the same denominator. Right? So therefore, um, this is x. If you want, you can write x out divided by xs. That is this, right? Which is equal to AF, the gain with feedback, which is equal to 1 over this value. So you excess you take here, you take this to that side and this side. So you do the multiplication. You have the gain with feedback, which is equal to A over 1 plus beta A. Okay, this is called the closed loop gain. We sometimes call it a closed loop CL, ACL. ACL. AF is also called ACL sometimes. Okay, right. And the loop gain, we call this beta times A, loop gain, beta times A. So sometimes we use the notation T. Sometimes we use with negative. We loop gain we minus beta A is considered as the loop gain. So what that means is, if you go through this loop, okay, you go through this loop, the gain will be minus beta times a. So for example, if xi, you start with this multiplied by a, this will be a times xi multiplied by beta, you will have beta a and times minus sign. So you have a negative sign here. So if you go through this whole loop, it will be minus beta. So this is called the loop gain. The loop gain is that much. Okay. All right. Um, okay. So now, since the time is up, we'll stop it at this point, and I will start from there the next day. Okay. So we'll start from there the next day, and we'll continue on feedback amplifiers. Okay. Thank you very much.
Thank you, sir.
Thank you.